Hello, physicists. These notes are going to be on the acceleration model that you actually derived in the It's All Downhill From Here labs. And so it's going to be mostly just review of what you should have already seen from the lab, but I definitely wanted to summarize so that we're all on the same page and ready to move on together. So open your notebook, get out your notes, and follow along. So the first thing that I want to talk about is that acceleration equals the change in velocity over time. So there's two ways to change velocity actually, because there's two pieces of information in velocity. There's how fast and direction. So you could actually be changing your velocity by changing your speed, and you can also be changing your velocity by changing your direction. Whee, acceleration. I'm changing my direction. But right now we're just looking at changing, having an acceleration due to a change in speed. So the first thing that we did in our It's All Downhill lab is we plotted position. Now I just want to note that I like to just call it position and use the variable p, but on the AP test they actually use the variable x if you're moving horizontally along the ground, or y if you're going up and down in the air, but I'm just going to keep it position because I'm lazy and I want to reuse these notes for my general physics class. So position versus time. We plotted position versus time and we did not see a straight line. We saw this curve up like that. So our position versus time graph was curved, so we had to do this little trick called linearization. So we linearized it, and linearization is actually huge on the AP test. So we linearized it by exploiting the fact that if we see this shape, it tells us that there's probably a relationship, a direct relationship, not between position and time, but position and time squared. So we graphed position versus time squared, and sure enough, we got this nice straight line. So the second one is linear here. So one of the big takeaways from this experiment is if you have acceleration, you get a curve on a position time graph. If you have constant speed, you get a straight line. And the reason for that is that the velocity, and we'll get into this later, but the velocity is the slope of a position time graph. So if you have a straight line, then the slope is not changing, so the velocity is not changing. If you have a curve, then that slope is changing. It starts out pretty flat here, and then it gets steeper and steeper and steeper and steeper. So this indicates acceleration, because we have a curve, a changing slope. So we linearized it to be position versus time squared, and then from here, we came up with a mathematical model. So we start with y equals mx plus b. The y turns into, I use p for position in general physics. AP students, you should probably use x for position, but I'm going to go ahead and use p on these notes. So p, y turns into p for position. Hopefully you guys saw from the lab that the slope was 1/2 the acceleration. So m turns into 1/2 a. And then x, well, what we graphed on the x-axis is not t, it's t squared. T squared plus a y-intercept of, well, whatever that initial position was, is where that y-intercept would be. All right, so this is actually a very famous formula for free fall. and that it's that the distance that this thing travels, if you take p minus p initial, you get distance. Distance that this thing travels is 1/2 at squared. Now, here's a quick note. If you start out with any initial velocity, this equation changes. So we purposely constrained this equation to have 0 initial velocity. So that is, we will get into having initial velocity in a few days. But right now, just know that this equation really only holds true for 0 initial velocity. Okay, so that's our mathematical model, and I would circle this. This is our mathematical model for the position of an object undergoing acceleration. Cool. All right. Then the next thing that we did in our lab was we graphed a velocity versus time graph. And we should have found a nice straight line because the only thing that we're doing in this class is constant acceleration. If it was a changing acceleration, we might have a curve, but for something like something falling down a ramp, it's actually just a nice constant acceleration. So we graph velocity versus time. And if you take a look at slope, slope would be the change in velocity over the change in time. Wait a second. Acceleration is the change in velocity over time. So the slope equals the acceleration. And in fact, that is the definition of acceleration, change in velocity over change in time. Okay, so our slope's the acceleration. So we can straight up use y equals mx plus b because guess what? This is linear. If it wasn't linear, we'd have to linearize it first, but since it is, go us. So the y turns into v because that's what's graphed on the y-axis. M is the acceleration because we just saw that the slope is the definition of acceleration. X is just straight up t. And b, well, if we started with some initial velocity, which we didn't, but if we had started with some initial velocity, we would have seen, maybe we would have seen a y-intercept. So I'll call it v little I. So that is a mathematical model for velocity with constant acceleration. So now I want to show you the last thing is how to move between the two. Oh, and in your lab, just one little clarification. So we should have seen that the slope is acceleration from our velocity time graph, and then you should have gone back to your first lab where we took the position time and saw that the slope of our position versus time squared was exactly 1/2 of our velocity versus time, and that's how you would conclude that position is 1/2 at squared. Instead of just AT squared. Just a subtle little add in there. All right. So the next thing that I want to talk about is how to go from from position time to velocity time graphs. So let's start out with this example because we've already seen it before. We've got position, we've got time, and we've got some acceleration, so it has this nice curve. So remember that velocity is the slope of a position time graph. So all I have to do to get a velocity time graph is I have to take a look at the slope. And so most of these are actually going to be qualitative. So when I look at this, I would look down here, I'd say the slope is about 0 down there, and it gets positive, velocity equals positive, and it's steep up here, and I can see that it's getting steeper and steeper and steeper. I also know that a velocity versus time graph needs to be a straight line. So I would estimate this. Now, if you were having to actually do quantitative, as in with numbers, you could draw in like a tiny little line here and find the rise and divide it by the run of several different tiny little lines that you draw in, right? Rise and run. So you could find the several little tiny different lines, and then you could plot those as data points. So you would find a time and a velocity, and you would plot them as data points on your velocity versus time graph. But for the most part, it's just looking at a general trend in the slopes. So the next thing I want you to do is you're going to do some practice problems or some prediction problems on the page next to these notes. So notes over here, and then these are going to be some prediction problems. So as you can see, there's a column for constant speed, position versus time graphs. Then there's a column for acceleration. And so speeding up, position versus time graphs. And then down here, we need to do velocity versus time graphs. So how we would read this is, so here's constant speed. Our first thing that we need to do is moving positive, position versus time. And then moving negative, position versus time. And then constant speed, velocity versus time, moving positive. Constant speed, velocity versus time, moving negative. And then motion diagrams down here. That's the dots with the arrows. All right, then under acceleration, we want to do speeding up, position versus time, which we probably should have already seen, moving positive. And then speeding up, position versus time, moving negative. What does that look like when you're moving negative? And then slowing down, moving positive. And slowing down, moving negative. And then velocity versus time, slowing down, speeding up, moving positive, slowing down, moving positive. So hopefully you guys can see that this is a grid. And so I want you guys to predict what all of those different types of motion is going to look like. One way that I predict how to do this is I think about the slope. If it's speeding up, our slope, so speeding up, slope goes from low to high. So it goes from less slope to a steeper slope. So if I'm speeding up positive, I might go from 0 slope up to a very steep slope, and then I can just kind of make it a curve. You know, if you're slowing down, it would be the exact opposite. So slowing down goes from steep to not steep. And I don't want to give it away, but you would start out over here as maybe as your 0 up here, and then start getting more and more steep as time goes on. So try to see if you can predict that. Now negative, remember negative, we would want to be looking at our slopes. So a positive slope looks like this. That might be a positive steep slope that gradually gets to no slope. A negative slope looks like this. That would be a negative steep slope that maybe gradually gets to a negative, no slope. So you just want to think about every second, is your slope getting steeper or shallower? If you're speeding up, your slope is getting steeper. If you're slowing down, your slope is getting shallower. If you're speeding up in the negative direction, your slope is getting steeper and more negative. If you're slowing down in the negative direction, your slope is getting less steep, is getting shallower and in the negative direction. So think about it. You do not have to be correct. I will go over these. You just need to try. So you just need to try to make a guess on these, and then we'll see if your prediction was right. So that's all I ask. Try to make a guess, and then guess first, and then see if your prediction was right. All right, good luck. You got this. Try your best.